Welcome to this coding problem walkthrough. In today's session, we'll explore the problem closest binary search tree value, a popular question involving binary search trees and efficient data retrieval. Let's get started by understanding the problem and breaking it down step by step. In this problem, you are given the root of a binary search tree, or BST, and a target value. The goal is to find the value in the BST that is closest to the given target. Now, let's break this down further. The input consists of two parts: first, the root of the BST, which is represented as a tree node object, and second, the target, which is a floating point number. The output will be an integer value from the BST that is closest to the target. If there happen to be multiple values in the tree that are equally close to the target, you can return any one of them. For example, consider a BST where the root is 4, with child nodes 2 and 5, and further children 1 and 3 under 2. With a target value of 3.714286, your task is to determine which node value is closest to this target. The correct output for this example would be 4, as it is the closest value to the target of 3.714286. To clarify, the distance between 4 and the target, which is approximately 0.2857, is smaller than the distance between the target and any other node value in the tree. Now, let's look at a simpler example with a BST containing just one node, 1. If the target value is 4.0, the closest value would obviously be 1, because it's the only node in the tree. Both examples illustrate the problem's requirements clearly: find the node value in the tree that minimizes the distance to the target. There are a few important constraints and additional notes to keep in mind. The number of nodes in the tree can range from 1 to 10,000. And each node value is guaranteed to be between 0 and 1 billion. The target value can range from -1 billion to +1 billion. Additionally, the BST property is crucial for solving this problem efficiently. Remember, in a BST, left child nodes are always less than the parent, and right child nodes are always greater. This structure allows us to use a guided search strategy rather than scanning all nodes. Some edge cases to consider include trees with a single node, targets that fall outside the range of all node values, targets that match a node value exactly, and skewed tree structures where all the nodes are on one side. Understanding these constraints and edge cases will help you design a robust solution. To solve the problem of finding the closest value in a binary search tree, one potential approach is brute force. The intuition behind this method is straightforward: traverse the entire tree and compare the absolute difference between each node's value and the target. During this traversal, we maintain a variable to track the closest value we've encountered. For instance, as we visit each node, we calculate how far its value is from the target and update our closest value if we find one that's closer. While simple, this approach has a time complexity of O(n), since we visit every single node, and its space complexity depends on the height of the tree, O(h), due to the recursion stack. However, the main trade-off here is inefficiency because it doesn't take advantage of the binary search tree structure, which could help us avoid unnecessary nodes during the search process. Now, we can improve upon the brute force approach by leveraging the binary search tree property. A BST is structured such that for any given node, all values in the left subtree are smaller, and all values in the right subtree are larger. This allows us to traverse more intelligently. Starting from the root, we keep track of the closest value encountered so far. At each step, we compare the target with the current node's value to decide where to go next. If the target is smaller, we move to the left child; if larger, we move to the right. This significantly reduces the number of nodes we need to visit. In terms of complexity, the time is proportional to the height of the tree, O(h), which is O log n, for a balanced tree but can degrade to O(n) for a skewed tree. Space complexity is O(1) for an iterative implementation, as we avoid recursion. By narrowing down the search space, this approach is faster and more efficient, though slightly more complex to implement compared to brute force. Another alternative is to perform an in-order traversal but with early stopping. The in-order traversal of a BST produces values in sorted order, and this property can help us stop the traversal as soon as we know further exploration is unnecessary. Specifically, as we traverse, we calculate the closest value so far. Once we encounter a node whose value exceeds the target, we can stop because subsequent values will only get further from the target. This approach is efficient in many cases since it doesn't require visiting all nodes, but its performance depends on the position of the target within the tree. The time complexity here is O, h plus k, where h is the tree's height and k is the number of nodes visited before stopping. Like the brute force approach, it requires O, h, space for the recursion stack, but it reduces unnecessary comparisons. While efficient, it requires careful logic to ensure the traversal stops correctly when the conditions are met. The strategy we've chosen is the optimized approach that leverages the BST property. The key realization here is that the BST structure acts like a built-in binary search, allowing us to home in on the target more quickly by deciding whether to move left or right at each step. This cuts down on unnecessary exploration. The aha moment comes from understanding that by simply comparing the target with the current node's value and adjusting our path accordingly, we can efficiently narrow down the search space. Compared to the brute force method, this approach avoids visiting all nodes, making it significantly faster. While the in-order traversal with early stopping is also valid, it may visit more nodes in certain cases and requires more complex stopping conditions. The optimized approach strikes the best balance between performance and clarity, making it the most intuitive and efficient solution for this problem. The optimized approach does come with some trade-offs. Its performance depends on the structure of the binary search tree. For a well-balanced BST, it achieves optimal time complexity of O log n, but for a degenerate tree that resembles a linked list, the performance degrades to O n. Additionally, implementing it iteratively requires careful pointer management, though this avoids the recursion stack overhead of a recursive solution. Overall, this approach stands out for its efficiency and elegance. It takes full advantage of the BST property to minimize computation and provides a clear, logical path to the solution. Given its strengths and minimal drawbacks, it is the most suitable choice for solving this problem effectively. To solve the problem of finding the closest value to a target in a binary search tree, we'll first examine a brute force approach. The idea here is straightforward: traverse the entire tree and calculate the absolute difference between each node's value and the target. By keeping track of the smallest difference encountered, we can identify the closest value. To implement this, we start by initializing two key variables. The first is closest, which will store the value of the node that is closest to the target. Initially, we set this to a very large value, such as infinity. The second variable is min_diff, which keeps track of the smallest absolute difference we've found so far, and it is also initialized to infinity. This setup allows us to systematically compare and update our results as we traverse the tree. Next, we perform a full tree traversal using either depth-first search, DFS, or breadth-first search, BFS. For each node we visit, we calculate the absolute difference between the node's value and the target using the formula diff equals abs, node.valueTarget. Then, we compare this diff with the current min_diff. If the newly calculated diff is smaller, we update min_diff to this new value and set closest to the current node's value. This ensures that the closest value is always being tracked as we progress. We continue this process for every node in the tree. Once the traversal is complete, the closest variable will contain the value closest to the target. Finally, we return closest as the result. It's also important to handle edge cases, such as when the tree is empty. In such cases, there's no value to compare, so we might return none or another appropriate default value. If the tree contains only a single node, the solution is straightforward because that node's value is inherently the closest to the target. Additionally, this algorithm works seamlessly with negative and fractional target values, as absolute difference calculations handle all numeric types. One key takeaway from this approach is that it guarantees correctness by visiting every single node in the tree. However, because it doesn't take advantage of the BST property, it doesn't offer any optimization over a regular binary tree traversal. To implement this approach, we use tracking variables like closest and min_diff to store intermediate results. For the traversal itself, we can use a stack for DFS or a queue for BFS, depending on the method chosen. The time complexity of this approach is O n, as we visit each node exactly once. The time complexity of O n arises because every node is visited during the traversal. Meanwhile, the space complexity depends on the traversal method. For DFS, the space complexity is O h, where h is the height of the tree, because it depends on the maximum depth of the recursion stack. For BFS, the space complexity relates to the maximum number of nodes at any level of the tree. To enhance this algorithm, we can exploit the properties of a BST. For example, if the target value is smaller than the current node's value, we can safely ignore the right subtree, as all values there will be larger. This reduces unnecessary traversals. By combining an iterative inner traversal with the BST property, we can efficiently find the closest value while skipping irrelevant nodes. Such optimizations significantly improve the algorithm's performance, especially for large trees. The solution employs an iterative approach to traverse the binary search tree, BST, and find the value closest to the given target. We initialize the closest variable with the root node's value. This value will be updated as we traverse the tree. Starting at the root, we compare the absolute difference between the current node's value and the target with the difference between the current closest value and the target. If the current node is closer, we update the closest variable. Since the BST property states that left children are smaller and right children are larger, we decide the traversal direction based on the target's value. If the target is smaller than the current node's value, we move to the left child, otherwise, we move to the right child. This process continues until we reach a leaf node, or none, at which point we've traversed the relevant portion of the tree and have the closest value stored in closest. The function then returns this value. The time complexity is O(h), where h is the height of the tree, because we traverse down a single path based on the target's value. For balanced trees, this is O log n, and for unbalanced trees, it can degrade to O(n). The space complexity is O(1), since the solution uses no additional data structures apart from variables to track the closest value. Here, we begin by defining a class called solution and implementing a method named closestValue. This method takes in two parameters, the root of a binary search tree and the target value, which is a double. The goal is to find the value in the tree that is closest to the target. We start by initializing a variable called closest to the root's value, assuming this is our best guess initially. Then, we use a while loop to traverse the tree, which continues as long as the current node, represented by root, is not null. Inside the loop, we check if the current node's value is closer to the target than the previously recorded closest value. If it is, we update closest to the current node's value. Next, we decide whether to move to the left or right child of the current node based on the relationship between the target and the current node's value. Specifically, if the target is smaller than the current value, we move left, otherwise, we move right. Finally, when the loop ends, we return the closest value, as it represents the value in the tree that is nearest to the target. Now, we see the definition of the treeNode class, which is the structure used to represent each node in the binary search tree. A treeNode instance has three components: an integer value val, a reference to the left child node, and a reference to the right child node. The first constructor initializes a node with only a value, and the left and right children are set to null by default. The second constructor allows us to initialize a node with a value as well as references to its left and right children. This class is essential for building and traversing the tree structure, as it defines the foundational elements needed for the closest value method to work effectively. In this example, we start with a binary search tree where the root node is 4, and the target value is 3.714. The first step is to initialize our traversal at the root. We set the closest value to the value of the root, which is 4, because that's our starting point. Now, in the first iteration, we compare the current node value, which is 4, to the target. The absolute difference between 4 and 3.714 is 0.286. Since this is our first comparison, the closest value remains 4. At this point, because the target is less than 4, we proceed to the left child, which is 2. Next, we arrive at the second iteration with the current node value of 2. The absolute difference between 2 and 3.714 is 1.714. This is a greater difference than the current closest value, which is still 4. Therefore, the closest value remains 4. Here, the target value is greater than 2, so we move to the right child, which is 3. In the third iteration, the current node value is 3. The absolute difference between 3 and 3.714 is 0.714, which is closer to the target than the previous node, but still not closer than our current closest value of 4. Since the target is greater than 3 and there is no right child for 3, the traversal stops. Ultimately, the closest value to 3.714 in this tree is 4. In this example, the binary search tree has 8 as the root, and the target value is 6. We begin by initializing at the root node, setting the closest value to 8. In the first iteration, we compute the absolute difference between the current node value, 8, and the target, 6. This difference is 2. Since no closer value has been found yet, the closest value remains 8. Because the target is less than 8, we move to the left child, which is 5. In the second iteration, the current node value is 5, and the absolute difference between 5 and 6 is 1. This is smaller than the previous difference, so we update the closest value to 5. Since the target is greater than 5, we proceed to the right child, which is 7. Now in the third iteration, the current node value is 7. The absolute difference between 7 and 6 is 1, which is equal to the current smallest difference. In such cases, we keep the first value we encountered within that difference. Therefore, the closest value remains 5. Since the target is less than 7 and 7 has no left child, the traversal ends. The closest value to 6 in this binary search tree is 5. For this example, the binary search tree is a skewed tree where each node has only a right child. The root value is 1, and the target value is 3.5. The traversal starts at the root, and the closest value is initialized to 1. In the first iteration, the current node value is 1, and the absolute difference between 1 and 3.5 is 2.5. Since no closer value is found yet, the closest value remains 1. Because the target is greater than 1, we move to the right child, which is 2. In the second iteration, the current node value is 2, and the absolute difference between 2 and 3.5 is 1.5, which is smaller than the previous difference. Therefore, we update the closest value to 2. Since the target is greater than 2, we proceed to the right child, which is 3. In the third iteration, the current node value is 3. The absolute difference between 3 and 3.5 is 0.5, which is smaller than the previous difference. So, we update the closest value to 3. Moving to the fourth iteration, the current node value is 4. The absolute difference between 4 and 3.5 is also 0.5, which is equal to the current smallest difference. By convention, we keep the first encountered value within the smallest difference, which means the closest value remains 3. Since the target is less than 4 and 4 has no left child, the traversal stops. The closest value to 3.5 in this binary search tree is 3. The time complexity of the closest value function is primarily influenced by the height of the binary search tree. This is because the algorithm navigates the tree in a top-down manner, deciding to move either left or right based on the target value. At each node, it performs a constant amount of work, such as comparing the absolute difference between the current node's value and the target, and updating the closest value if necessary. This constant work is O(1) per node. Now, the height of the tree determines how many nodes are visited during the traversal. In the best case, where the tree is perfectly balanced, the height is O log n, since the search space is halved with each level. However, in the worst case, such as an unbalanced tree that behaves like a linked list, the height becomes O n. Therefore, the time complexity ranges from O log n in the best and average cases to O n in the worst case, depending on the tree's structure. The space complexity of the closest value function is straightforward to analyze because the algorithm is iterative, avoiding the overhead of a recursive call stack. It uses a constant amount of additional memory, as it only needs a few variables to keep track of the current node, the closest value, and the target. These variables require O(1) space. Additionally, the function does not utilize any external data structures, like stacks, queues, or arrays, which further simplifies the analysis. As a result, the space complexity remains constant at O(1) in all cases, regardless of the tree shape or size. When comparing the optimized closest value function to a naive approach, the differences in efficiency become clear. A naive approach would involve traversing the entire tree, calculating the absolute difference for every node. This method results in a time complexity of O(n), because every node is visited, regardless of the target value or the tree structure. However, the space complexity remains 1, as no additional data structures are used. In contrast, the optimized solution takes advantage of the binary search tree property to reduce the search space by moving either left or right based on the target. This reduces the time complexity to O log n for balanced trees, while still maintaining O space complexity. For unbalanced trees, the time complexity is equivalent to the naive approach at O(n), but the optimized solution is more efficient overall for typical cases. To solidify the time complexity analysis, let's consider the mathematical reasoning. In a balanced binary search tree, the height of the tree is approximately log_2 n. Since the algorithm performs one comparison and a single branch traversal at each level, the total number of steps is proportional to the height, resulting in O log n operations. However, in an unbalanced tree, where the height could extend up to n in the worst case, the number of steps becomes O(n). Overall, the optimized solution is highly efficient for balanced trees, offering logarithmic performance, while still being robust enough to handle unbalanced trees, albeit with linear time complexity in such cases. When solving problems involving binary search trees, it's important to avoid certain common pitfalls. One frequent mistake is not taking advantage of the BST sorted structure. Treating the BST as a generic binary tree and traversing all nodes can lead to inefficient solutions, as this ignores the optimizations that a BST inherently provides. Another issue arises when recursive solutions are implemented without proper base cases, such as failing to handle none nodes or neglecting to check value ranges. This can result in runtime errors or unexpected behavior. Additionally, some candidates try to store all node values in an array and use operations like sorting or linear search to find the closest value. While this might work, it's unnecessarily slow and defeats the purpose of working with a BST. For problems involving floating point comparisons, precision errors can be problematic, especially if absolute differences aren't used for comparisons. Finally, it's critical to remember that not all BSTs are complete or balanced. Making this incorrect assumption can lead to errors in time complexity analysis or recursive depth handling. To excel in BST-related problems during interviews, it's crucial to recognize patterns and leverage the tree's sorted structure. Many problems can be simplified by focusing only on the relevant subtree, left or right, based on the target value. Additionally, you should be comfortable implementing both iterative and recursive solutions. While recursive solutions are often more intuitive, iterative approaches save space by avoiding the function call stack, though they may require more careful management of edge cases. For more advanced tasks, like finding the k closest values, consider combining traversal methods with data structures like priority queues or sliding windows for optimal efficiency. Always clarify the input details with the interviewer, such as whether the BST is balanced, whether duplicates are allowed, or what the input value ranges are. These clarifications can significantly impact the approach you take. Finally, practicing related problems, such as searching, inserting, or validating BSTs, will help you build a strong foundation and recognize recurring techniques. Different approaches can be used depending on the problem requirements and constraints. A brute force traversal is the simplest method, where you traverse the entire tree and compute results. While straightforward, this approach is inefficient, with O(n) time complexity, and it doesn't utilize the BST structure. A more efficient method is binary search within the BST, which allows you to directly navigate to the most relevant nodes using the tree's properties. This approach achieves O(h) time complexity but requires a careful and precise implementation. Alternatively, an inner traversal can be used to access the values in sorted order, which is particularly helpful for problems that involve processing sorted data. However, this may incur higher space complexity due to storing the traversal result. Finally, for advanced problems, you can augment the BST with additional information, such as subtree sizes, to facilitate more efficient queries. While this adds complexity to the tree operations, it enables powerful and optimized solutions for certain types of problems. Great job reaching the end of this problem walkthrough. To recap, we reviewed efficient strategies for solving the closest binary search tree value problem and highlighted key concepts from binary search trees. Don't forget to practice similar problems to strengthen your understanding, and stay tuned for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!